All right, AP Chemistry. So this assignment, day 12, is an introduction to stoichiometry. And we've done some dimensional analysis with the Usain Bolt problem, the one with all the student names in it. So now you're going to actually apply that to chemistry. And these next two assignments, day 12 as well as day 13, 14, are going to simply deal with two units of measure, grams and moles. So you only have to focus on those two. And I'll show you a graphic organizer that we'll use to help us kind of keep this straight. So your pre-assignment reading was to do this. So let's just go over this. So stoichiometry is the study of conversions from the language of chemical equations to measures that we make in the real world, such as grams of solid or liters of gases. A mole is 6.022 times 10 to the 23rd. Usually this refers to a number of atoms or molecules. A chemical equation can be read. So we talked about the different ways you can read a chemical equation. So you can either read this as 2 molecules of hydrogen plus 1 molecule of O2 gives you 2 molecules of H2O. So that's one way to look at this. It's just on the molecular or atomic level. What a chemical equation is doing, it's matching up numbers of atoms or molecules, not weights, not masses. It wants numbers. Just like my example in class where I wanted to have groups of 1 senior and 2 juniors, but if I couldn't see them, I had to use their weights to determine who was a senior, who was a junior. That's an analogy to what we're doing here. Now, if we can't see atoms and molecules. They're too small. So if we multiply everything by a very large number, 6.022 times 10 to the 23rd, we can read the same equation as 2 moles of H2 plus 1 mole of O2 will produce 2 moles of H2O. So 2 times 6.022 times 10 to the 23rd plus 1 times 6.022 times 10 to the 23rd will produce water molecules 2 times 6.022 times 10 to the 23rd. So now we have big baskets of molecules that we can now see and weigh, enough to be able to see and weigh. So we can actually see and weigh 1 mole of H2O, so the equation is speaking to us in amounts that we can use in the real world. Again, the way you want to think of these in general is as a relationship. I need twice as many molecules of hydrogen as I need molecules of O2. So if I use 1.3 molecules or moles of H2, I need, let me say that again. If I need 2.6 molecules of H2, I need half that many, 1.3 molecules of O2. You could look at it in the other direction. If I have 5 molecules of O2, I need twice that many. I need 10 molecules of H2 or 10 moles of H2. Okay, so it's just a relationship 2 to 1. These can be any numbers, but it's just that this number has to be twice as much as this number, and this number will be the same as this number since they both have coefficients of 2. Whatever number of moles of H2 I used, I will end up with that same number of moles of H2O. So molar mass. But we still can't count a mole of atoms or molecules. So an atom or molecule is too small, a mole is too big. We can't count that. So how do we know we have a mole? We do this by using the mass in grams of 1 mole of an atom or molecule. Here are the molar masses. It means the mass of a mole of something, of some common atoms, molecules. So 1 mole of hydrogen, you get this off the periodic table. 1 hydrogen atom is 1.01 atomic mass units. We'll almost never use the term atomic mass unit again. 1 mole of hydrogen is 1.01 grams. That's something we can measure on a scale. 1 mole of H2O is 18.02 grams. 1 mole of CH4 is 16.05 grams. So those are all measures that we can weigh on a scale. Because we can measure grams on a triple beam scale, we can calculate the number of moles. So the scale allows us to measure grams. Over here we have the chemical equation, which gives us relationships between numbers of these molecules. And the translator that gets us from grams to moles, or from moles back to grams, is called the molar mass. That relates moles the equation uses to grams that people use. So here's a molar mass for water. We can weigh 18.02 grams on the scale and know that we have exactly 1 mole of water over here. All right, so We're going to now move on and do some one-step problems. These will be very straightforward. I don't give you a whole lot of them because I think you'll catch on to them very quickly. I'll do a couple from each of the two chemical formulas here. Okay, so here we go. So here we have a chemical formula, and this is the graphic organizer that you will be using. And inside the dashed line is the world of the chemical formula. Again, it's counting numbers of particles. It needs two atoms of silver for every 1 molecule of H2S. Okay, if this is 100, then this has to be 200. If this is 50, then this has to be 100. It's a 2-to-1 relationship between those. So we're going to put different numbers of moles down here, and you're going to see how those relationships work. Now, we can't count these numbers of moles. So out here is our world. That's what the little children represent. We're in our world. We can measure things on the scale in grams. Okay, so we have grams, but the chemical equation doesn't care about weight. It doesn't deal in weight. So we have these translators to get us from grams down here to moles up here, or back the other direction, from moles up here back down to grams here. And you have one for each of the substances here. These do not change. If you did another problem with silver, it would be 1 mole equals 107.9. I think that's actually 87 we used in class. Let me just change that one. So 107.87. If you did another problem with H2, it would be 1 mole of H2 is 2.02 grams. Now don't make this mistake. Molar masses are always 1 mole equals some number of grams. The 2 up here is only for this specific chemical equation, and it will relate silver to these other substances here. Don't use the 2 for the molar mass. Don't take the 107 and multiply it by 2. The molar mass of a substance is always the same. It's always 1 mole of that substance equals some number of grams. Okay, so what we're going to do is we're going to get started. These are all one conversion problems. They're all moles to moles. So the first one says, how many moles of H2S? So this is what we're looking for. That's our question mark. We're trying to find that. Are required to produce 3.5 moles of Ag2S. So this is what we know. This is what we're trying to find. So we're now writing a math equation. So over here on the right, we have moles of H2S. That's what we're trying to find. So this is where our answer will go. And over here, we put what we know over here. So it's 3.5 moles of Ag2S. Okay, so the question mark moles of H2S goes right here. Here's H2S, here's the moles row, so the question mark goes there. That's what we're trying to find. Moles of Ag2S, 3.5, here's moles row, and here's Ag2S, so the 3.5 goes there. So it's only one conversion to get between these two, and that's a moles to moles conversion. Now, what is that? Well, it's simply, the equivalency is simply this equals this. That's how you get your equivalency for moles to moles. It's very easy, and you just put an equal sign between them. But you have to add the word mole, so 1 mole H2S equals 1 mole Ag2S. That's all you do for the equivalency. Alright, so I'm going to write the equivalency over here. Okay, so this equates the two of them. Again, it's practically already written for you right here. You just have to add the word mole and put an equal sign between them. Okay, so now we're going to write our 2 conversion. By the way, we've seen that by the graphic organizer that it's a one-step conversion, so we put a single box here. So now we're going to write our 2 conversion factors. This over this. Doesn't matter which one goes first. Or you flip it. This over this. Okay, there you go. So now you have to choose one of these. These are both true statements. Remember, we talked about that. These are both true statements. There's 1 mole of H2S for every 1 mole of Ag2S, or there's 1 mole of Ag2S for every 1 mole of H2S. Those are both true statements. But only one of them is going to fit in there to get our units to cancel properly. So which one is it? Think about it. Okay, so the answer is we need moles of Ag2S to cancel because they don't appear in the final answer. So we need Ag2S down here. Another way you could have thought of it is we have moles of H2S in the final answer, so we need moles of H2S up on the top here. So that's going to be this conversion factor right there. So we're going to write that here. Okay, so moles of Ag2S cancels with moles of Ag2S. The last man standing, moles of H2S, is what's in the final answer. Whatever you haven't canceled out over here, the only thing you didn't cancel out is moles of H2S. That's what appears in your final answer. So this is a real easy one. 3.5 times 1, you multiply everything on the top, 3.5 times 1, and divide by everything on the bottom, divided by 1. And of course that just gives you 3.5. So 3.5 moles of Ag2S will produce 3.5 moles, or you can produce 3.5 moles of Ag2S from 3.5 moles of H2S. Notice those two numbers are the same. That's called a one-to-one relationship, okay? 1 mole of this produces 1 mole of this. 3.5 moles of this produces 3.5 moles of that. So that's, even though the number's 3.5, you still call it a one-to-one relationship. There's 1 mole of the first one for 1 mole of the second one. Okay. Let's go ahead and do this. Alright, so what I'm going to do first of all is I'm going to clean up my graphic organizer up here. Do a lot of lines up here and question marks. I want to reuse that. So again, this is just reusable for you to do. Don't write too hard. Definitely don't write in ink. Okay, let's go on to B. How many moles of H2 will be produced by 5.41 moles of Ag? So what we're trying to find is moles of H2. So I'm going to come way over here and I'm going to write some underline mole of H2. So that's where my answer is going to go. I'm going to put an equal sign there. And we're starting off with 5.41 moles of Ag. So I'll come here. Okay. And so we're going to go up to our graphic organizer. So moles of Ag is right here, and there's 5.41. And moles of H2 is over here. That's what we're trying to find. That's our question mark. So it's a moles to moles conversion. That's a one step, okay? You don't worry about these. You're not interested in these right now. So it's a one step going from moles here to moles here. And your relationship, your equivalency, again, is just the coefficient and the substance. You put the word mole in there, equals this coefficient and this substance. So I'll write it out down below, but you get to where you don't even have to do that. You just see that relationship. So it's going to be, write it over here. Okay, so there's the equivalency. By the way, you're not worried about the states of matter here. There are going to come a time later in this class where that is an issue, but this is simply solid, solid, solid gas. We don't care about that. Okay, now the conversion factors is just one over the other. Doesn't matter which one you do first. Or we're going to flip it. These are both true statements. Crowding myself a little bit here. So let me draw my box so I can kind of save my space for this. I'm going to write this over here. Okay, so there's one of my conversion factors and there's the second one. So which one of these two is going to go in that box up there? Think about it. Okay, so we have moles of silver, moles of Ag, doesn't appear in the final answer, so this has to cancel out. That means we need it down here on the bottom. We need moles of H2 in our final answer. That means it needs to be up on the top, so it's going to be this one right here. Okay, moles of Ag, moles of Ag. So it's 5.41 times 1 divided by 2. Again, it's everything on the top. 5.14 times 1 divided by 2. That gives us 2.71. Not going to worry too much about significant figures. I want you to focus on the stoichiometry here. Okay, that would be a proper number of significant figures, though. So that's your answer for that one. Okay. All right, I'm going to do a couple from the next one. They're done exactly the same way. I'm going to leave these two for you to do, so I'm going to give you the answers to those. Okay, so now we're looking at a combustion reaction. This is a hydrocarbon called ethylene. Hydrocarbons are always CH compounds, and you're burning it. You're combusting it. It's called a combustion reaction. Combustion reactions are always some hydrocarbon. There's a whole lot of different hydrocarbons, plus oxygen. You're burning something. You need oxygen. You have to light a match to it. And that's going to produce carbon dioxide and water. Okay, so combustion reactions always look like this. The only thing that's different is you use different hydrocarbons and it balances differently. You'll have different coefficients, but they all look like that. So you need to convert, calculate the molar masses, and I very rudely did not leave you space to do that here, so I'm going to do it up towards the top. So CH4 is going to be, or C2H4, excuse me, is going to be, it's going to be carbon. You have 2 times, and off your periodic table, 12.01 grams. Okay. All right, and you get that straight off your periodic table below carbon. Then you have H. You have 4 of those, that's what the subscript says, times, off the periodic table says 1.01 grams. Again, periodic table is either atomic mass units or grams for the mass, but we're dealing with moles, so we're going to call it grams. So when you multiply this, you get, and what you'll then get is 28.06 grams per mole of C2H4. So I'm going to write that right here. I didn't leave really a lot of space there, but I'm going to put 28.06, so that goes right there, grams, okay? O2. Now here's the thing not to get confused with. It's not 3O2 when you're computing molar mass. This is number of moles of O2 for this specific chemical equation. But in general, what you want for molar mass is just 1 mole of O2. So if you look at your periodic table, you will see that oxygen is 16 and 2 of them is 32. So you do multiply by this number. We're talking about O2 molecules. They have a mass of 32. So we're going to put that up here, 32, and it's actually 0.00 grams. So if you have an O2 molecule, if this was just an oxygen atom, 1, then that would be 16. If you have 2 of them, it's 32. But you don't multiply by the coefficient. This coefficient applies only to this specific chemical reaction. You're interested in 1 mole of O2 molecules. Okay, so that's 32. CO2, same thing. Carbon is 12.01. Oxygen, we just said, is 32. You add that together, you get 44.01 grams for carbon dioxide. So you do count these oxygen twice. 1 carbon, 2 oxygen, but you do not count this. This is 2 moles of CO2. Molar mass is always 1 mole of CO2. Okay, so don't ever forget that. In other words, the molar mass for carbon dioxide in any problem you ever work is always going to be 1 mole CO2 equals 44.01 grams. It doesn't matter what this coefficient is, what these coefficients up here are. These are just for this specific reaction. Okay. H2O is 18.02. It's 2 hydrogen at 1.01 times 2 plus 16 for 1 oxygen atom. This time it's not an O2. It's 1 oxygen atom is 16. 16 plus 2.02 for those two is going to be 18.02. Again, you totally ignore these coefficients when you're computing molar mass. Okay? So any problem you ever do, the molar mass of O2 is going to be 32. No matter what this coefficient is here, it's going to be 32. All right? Okay, so now, first question. How many moles of H2O will be produced by 3.51 moles of C2H4? So what we're looking for is moles of H2O. I'm going to come over here. There's mole of H2O. And they're going to be produced by 3.51. Okay, so the question mark that we're trying to find is moles of H2O. So that's right here. And what we're starting with is 3.51 moles of C2H4, so the 3.51 goes here. This is very similar to the last problem. So what we're starting here, and we want to end up here, that's a single conversion. It's moles to moles. And you're not interested in these two, you just skip over them. It's a single conversion that relates 1 mole of C2H4 equals 2 moles of H2O. And that's going to be your equivalency, and then you're going to build your conversion factors from that. So let's go ahead and write that equivalency, 1 mole. The only thing you have to add between this and this is the word mole. Okay, there's the equivalency between this and this. Now you put one over the other and then you flip it. Okay, I'm going to come over here and do that. a little more space. Let me go ahead, since it's a one conversion. Again, that's what the graphic organizer tells us. If you weren't sure of that, eventually you'll get to where you can recognize that without looking at the graphic organizer. So it's one box. So we'll come make our equivalencies here. And I'm going to cheat down into this space since I'm not going to do these problems for you. You might want to do this on line paper. I really should have left more space here. Or if you want to download the Word copy of this assignment, you can come in and put more spaces in there. You can edit it and do that. That's up to you. Okay, so you're going to pick one of these two to go in that box. Which one is it going to be? You have moles of C2H4 here. That doesn't appear in your final answer, so that has to cancel out. So you need it down here on the bottom, so this will cancel out. You need moles of H2O on the top here because it's going to appear in your final answer, so you are going to choose this one. Moles of C2H4 cancel, cancel. Last man standing is moles of H2O. So you have 3.51 times 2 divided by 1, and that's going to give you 7.02. Moles of H2O. And that's your final answer, okay? So you are going to go ahead and do the rest of these, and I will give you the answers to those. Alright, so here are your answers for B, C, and D. D's worded a little differently. How many moles of O2 are required to completely combust, that's burn, 2.11 moles of C2H4? So what the equation is telling you very simply is you need 3 times as many moles of O2 as moles of C2H4. So it tells you the number of moles of C2H4. You got to figure out how many moles of O2. Okay? So we'll do that one. We can do that one in class if you need help on that. But there are the answers to these 3. Alright, so the final page involves some review problems, and I tell you where you can go to find information on these. So this is from Lesson 10. And it's just, I want you to be familiar with the different ways that you might see molar mass and the different ways it can be expressed. So you're not used to seeing it just one way, but if you see it a different way in a problem on the AP exam, you won't recognize it. Okay, so I'm only going to do one of these. You do the other two. So I'm going to do NO3. So nitrogen, you have one of those. Oxygen, you have 3 of those. Okay, and you add that up. So 3 times 16 is 48. 1 times 14.01 is 14.01. So you add those to 48 plus 14.01. And that's going to give you 62.01. And that's grams for 1 mole of nitrogen. So I'm going to write it like this. 1 mole equals that. So the equivalency, to write it out properly, 1 mole of nitrogen trioxide equals okay, so that's the equivalency. You're just equating the grams to the moles of that substance. The shorthand, the way that you would see it in a problem is like this. That it is 62.01 grams per mole. So be used to seeing it that way and know that you can turn that into an equivalency like that. 62.01 grams per mole. There's an implied 1 on the bottom, so 62.01 grams per every 1 mole. Okay? So the conversion factors here, you would simply do what we've done before here. Okay, now you can plug one of those two into your stoichiometry equation depending on which one is the appropriate one. So I just want to be sure you know all the different ways that you can see. First, compute the molar mass, write the equivalency, show the shorthand, which is what you'll usually see in a problem on the AP written like that, and then know how to take the equivalency and convert to conversion factors. You can do the other two here. I said you could do the calculations down there, so I gave you a little space for that. Okay. Here's one that some students have had issues with. It's the naming of ionic compounds. So an ionic compound is a metal. The metal always comes first. And a nonmetal, that's a strong guy and a weak guy. And the nonmetal is going to take an electron or 2 or 3 away from the metal. Okay? So the first thing you do is you get the charge number here. So calcium. You can get your charge number by ion sheet. It's the pink sheet in your packet, or the 60 common ions. That's the kind of the striped sheet. They're about the second and third sheets in your packet. But you should be able to do these just by looking at a periodic table. So here's calcium. So it wants to ionize to be like the nearest noble gas. So where's the nearest noble gas? Well, in its own row, it's krypton. That's way over across the periodic table. And you have to count all those elements across to how far that is from calcium, krypton and calcium. Or calcium can go backwards and be like the noble gas in the row before, argon. That's quicker and easier for it. So how does it do that? It loses 2 electrons. So it loses 1 electron. It has the electron configuration of potassium. It loses 2. It has the electron configuration of argon. It has 2 electrons. It has 2 electrons in its outer orbital, its 4th orbital. And if it loses those 2, then it no longer has a 4th orbital. It only has a 3rd orbital. And that 3rd orbital is filled. Okay, so go back and do a diagram of calcium if this is kind of, still not really clear to you. So this wants to give up 2 electrons. That's going to give it a positive charge. It's going to have 2 more protons than electrons. Okay, so calcium becomes a 2+ charge. Chlorine. To be like the nearest noble gas, this chlorine, it just has to gain 1 electron to become like argon. 1 more electron. It has 7 because it's the 7th element in its row. If it gains 1 more, it has 8. It's going to be like argon. It wants to be like argon. It certainly doesn't want to go backwards to neon because that's way back across the periodic table. So it's going to gain 1 electron. So that means it's going to be a -1 anion. Okay, negatively charged ion. -1 because it gains 1 more electron. It has 1 more electron than proton once it gains that electron. So it's going to be Cl1-. Okay, so an ionic compound has to be charge balanced. So this one is a 2+, this is only a 1-. You need another one of these. Put another way, this calcium is going to give off 2 electrons. We just said that. This chlorine can only catch 1. So you're going to need a second chlorine. Okay, so you're going to need 2 chlorines. That'll give you a 2-, and calcium is a 2+, so 2+, 2- balances. The way you do it with the crossing arrows method, very simply, is this 1, forget about the negative sign, just bring the 1 down there, and the 2 you bring down there. You crisscross them over. So that's going to be Ca1, but you don't write 1s for subscripts. And then it's chlorine 2, Cl2. Okay, so you have 2 of the 1- is 2-, and 1 of the 2+, that's 2+, 2+, 2- balance out. And the name for this, the way ionic compounds are named, is calcium. The metal, Ca, keeps its name. And the nonmetal, the anion, changes the end of its name to IDE. So it's calcium chloride. Okay, and that's all you do for that. Okay. Now, I'm going to do this one. Now, for this one, you do need either your charge number by ion sheet, the pink sheet, it's the second one in your packet, or the 60 common ions, which is the 3rd sheet in your packet. Because iron can either be a 2+ or a 3+. It's right here on the periodic table. You can't figure out what its charge is going to be the way you can for the first 2 columns or the last 6. Where these 2 are either going to lose an electron or lose 2 electrons, or these over here are going to gain 3, gain 2, gain 1 to be like the nearest noble gas. You can't figure it out. You have to have the sheet that tells you what the charges are for iron. And those are going to be either 2+ or 3+. Iron can either lose 2 electrons or 3 electrons. So you have to be told which it is in order to do this problem. Okay, so this is an iron 2+. It's going to lose 2 electrons. This is an oxygen, so let's write that up here. Iron, Fe, is a 2+. Again, either your charge number by ion, pink sheet, or your striped sheet, the 60 common ions, will tell you that. But we're choosing the 2+ one. Okay, oxygen. Okay, so again, oxygen, to be like the nearest noble gas, neon, It has 6 electrons. We know that because it's the 6 valence electrons, because it's 1, 2, 3, 4, 5, 6th position over. It wants to fill its valence orbital. That means it wants to gain 2 electrons, so it's like neon. Everybody wants to be like a noble gas. So it gains 1, 2 electrons, so that's a 2 minus. Remember, electrons are negative, so when you add electrons, you're adding negative signs. So it's a 2 minus that it becomes. So the oxygen is 2 minus. Okay, so this one is easy because you have a 2 plus matched up with a 2 minus. So this 2 comes over here. This 2 comes over here. So you have Fe 2 O2. You have 2 Fe's for every 2 O's. But you can reduce that just like you reduce a fraction. So it's just simply going to be Fe O. Okay, there's 1 oxygen for every 1 iron. Okay, now the name, you have to include that charge. If it has more than 1 charge, you have to include that as a Roman numeral. So the name of this is going to be iron, parenthesis, Roman numeral 2, and then oxide, IDE at the end of oxygen. So iron 2 oxide is the way that you would read that. Okay, same with copper. So you want to look up, see what copper's charges are. These 2 are going to be just like this one up here. They don't have, there's only 1 charge potassium can have and only 1 charge nitrogen can have. So go ahead and do those. Okay, that takes care of it for this lesson.